All right, in this problem, we look at an example of cylindrical coordinates being used to find the volume of a particular region. Okay, 65 is a great example of where cylindrical coordinates could come in real handy. Okay, we're doing a volume type integral, so we need to be doing a triple integral over a region or domain D of three-dimensional space. We're integrating the function 1 and we're integrating with respect to dv. Okay, now dv we know could be dz, dy, dx if you choose to go the rectangular coordinates route. But if we choose to set this problem up in another coordinate system, like cylindrical coordinates, cylindrical coordinates, dv would be r, dr, d theta, dz. And the reason that this r is here is to correct the units. Dr is a radius measurement, the radius of a circle perhaps, so that's measured in meters. Z and the cylindrical coordinates is the height of a cylinder, also measured in meters, but theta is something measured in radians, and so what we need is to get an angle measurement, which is somewhat dimensionless, and we need the fudge factor, the radius again, to be measured in meters, so that the whole dV comes out to be the units of volume, meter cubed. Okay, so if we were trying to do this volume integral here in terms of cylindrical coordinates or rectangular coordinates, one setup could be easier than the other. We can see here that we'd be integrating from z on the bottom up to z on the top, and the function z changes from x squared plus y squared squared minus 1 on the bottom to z is equal to 4 minus 4 times x squared plus y squared on the top. So we have two different paraboloids, one on the top, one on the bottom, and that could be your z integral, right? And then if you tried to stay in rectangular coordinates, we would have to look at what's going on in the xy plane, right? In the xy plane, we would need to be looking at when these two paraboloids intersect each other, and we can see that they intersect each other when, let's see, when their z values are the same, okay? And we can see that they intersect in the z equals 0 plane, so that when the top paraboloid, when z is equal to 0, that tells us that 4 is equal to 4 times x squared plus y squared, okay? And that happens when x squared plus y squared is equal to 1. Okay, we can also see the same thing in the other when z is equal to 0. For the other equation, you get x squared plus y squared squared minus 1 is equal to 0. And that is also x squared plus y squared is equal to 1. So these two paraboloids intersect in the z equals 0 plane at this circle, x squared plus y squared is equal to 1. And then that would say that if we wanted to find the volume of the region, y would need to go from, on the bottom, negative square root of 1 minus x squared, up on the top to the square root of 1 minus x squared. Okay, and that's what would go here and here in the y limits of integration, and then x would go from negative 1 to 1. Okay, so this might be an easy integral to write down, but it might be another thing to evaluate it, right? And we know that in these problems, one reason we are changing coordinates is to make our lives easier when it comes to integration. So if we switch to cylindrical coordinates, we would have dz, dr, d theta, with r being the fudge factor to make the dv units come out to be volume units. We can see that z would go on the bottom from x squared plus y squared in cylindrical coordinates is r squared, so that would be r to the fourth minus 1 on the bottom, to z is equal to 4 minus 4r squared on the top. Okay, the radius would go from 0 to 1. Okay, we can see this region being described in terms of circles of increasing radii, and then theta would be going all the way around to make the whole region. So theta would go from 0 to 2 pi. Okay. Now both of those integrals should evaluate to the same thing. So here we have set up the two integrals. Sorry, let me bring up just so you can see Palette Writing Assistant. Let's set up these integrals. Okay, we'll put them both in and make sure that they come out to be the same value. So here's our integral for rectangular coordinates. Here will be our integral for cylindrical coordinates. So we're going to integrate 1. We've got dz, dy, dx. We've decided that z is going from x squared plus y squared squared minus 1 on the bottom, that paraboloid on the bottom, up to 4 minus 4 times x squared plus y squared on the top. And then, let's see, this is where it gets a little complicated to type. Y went from negative square root of 1 minus x squared on the bottom. If we persist with rectangular coordinates, we're going to get some nasty square roots in the problem that we may not like having to deal with integration-wise. But here we are setting it up nonetheless, negative 1 to 1 for x. So that is the integral in rectangular coordinates. In cylindrical coordinates, we would integrate r because of the fudge factor. Right, the fudge factor right here. Let's see, dz would be a function of the other cylindrical coordinates, r and theta. So in this case, z goes from r to the fourth minus 1 up to 4 minus 4 times r squared. Okay, we could then go to the r integral and then the theta integral. R, we're seeing, goes from 0 to 1 because we've sketched the region of integration in the xy plane, and theta goes from 0 to 2 pi. So if we evaluate both of these integrals, this one may be hard to compute by hand, but the computer handled it and didn't seem to take too long to compute it. This is the easier integral to do by hand, is pretty easy. Okay, and when you evaluate this integral by hand, you get the same answer, 8 pi over 3. Okay, so there is a good example of using cylindrical coordinates to evaluate a volume integral over a region that doesn't necessarily look cylindrical. What is really a tip-off that you should do cylindrical coordinates in this problem is that we have a circular region where in the xy plane that we need to integrate over, and z we can just handle as z as if it were a normal Cartesian coordinates problem or rectangular coordinates problem. So there we have an example worked out completely.